Hello, everyone. Thank you for taking the time to interview with us and talk a little bit more about your work on using our SilcoTek 2000 coating to help prevent jet fuel oxidation. So before we proceed, I just wanted to give a brief interview. You guys are graduate students for Professor Miljkovic at UIUC in the College of Engineering. And we've had email communications on and off for a few years, discussing about coating options to help you combat jet fuel oxidation. So my very first question is, in your recent publication where you compared the jet fuel oxidation performance between conventional manufactured metal tubes versus additively manufactured metal tubes, my first question is, what kind of parts are usually conventional manufactured and what sort of vulnerabilities they usually face?
So, modern aircrafts are designed to fly at high Mach numbers, but with high heat loads, there is a possibility of heat generation inside the heat exchanger systems of the jet fuel propulsion system. So usually what happens is people are like researchers are or people are using jet fuel as a coolant as well as a propellant. So for these heat exchanger systems, usually conventionally manufactured tubes are utilized. So these conventionally manufactured tubes in jet fuel systems is typically produced through processes like extrusion, machining, or welding. So these methods usually create relatively smooth internal surfaces, but they often suffer from like limitations such as restricted design flexibility and also difficulty in optimizing heat transfer properties and also increased weight due to material constraints. Additionally, traditional manufacturing methods may require multiple components to be joined together, which can introduce like potential weak points for oxidation and like fouling buildup. So these are the vulnerabilities that can be created when we use traditional or conventionally manufactured tubes.
I see. Well, thank you very much for explaining that. So, can you explain the additive manufacturing process and what sort of issues does that solve that usually faces the conventional manufacturing?
I can take that question. So additive manufacturing is essentially a process where instead of taking a big block of material and then converting it into a part, you start making your part layer by layer. So it's like making a cake where you build it layer by layer, add frosting, add all those different layers that you would do in a cake, and that's what additive manufacturing is. As a process itself, it gives you a lot of freedom in the in terms of design flexibility, in terms of complexity of the design that you could make. It reduces the number of moving parts in your system. It reduces the number of points where failure could occur, failure both mechanical as well as in terms of oxidation of jet fuel in our context. And it produces relatively lesser waste when it comes to the aviation industry because you're using expensive metals like titanium. And additive manufacturing uses lesser material because you're not really cutting down and reducing waste, but you're building from down to up, if I can say that.
So it's a more economic process.
Right. It is very economical and it's very upcoming. So, even though it's not perfect right now, there's a lot of people in the world, a lot of research going on, working to make additive manufacturing as a whole better. And, it holds a lot of promise.
Okay, yeah. So as you just mentioned, additive manufacturing is not yet perfect. As you guys describe in the paper, their surface roughness seems to be higher from the additively manufactured parts. So what sort of materials did you consider to combat fouling with additively manufactured parts?
I can take that. So one of the biggest challenges of additive manufacturing is its inherently like rough surface texture, which can promote jet fuel fouling by increasing surface area and providing more nucleation sites for carbon deposition. So to mitigate this issue, the research team considered surface coatings which can withstand like high temperature fluctuations and also which can resist any kind of chemical attacks inside it. So such coatings, for example, Silcolloid 2000, which is basically a silicon-based coating, has high fouling resistant properties. So other potential materials can include ceramic-based coatings. Then we have hydrophobic treatments and engineered superalloys that can be designed to withstand these oxidation and resist fouling in extreme conditions or environments.
Okay, so basically you need a surface that is thermally stable at the temperature where fouling forms and also chemically inert. So what industry or companies that can benefit from those additively manufactured parts?
I could answer that question. So additive manufacturing as a process itself, it's not really limited to specific industries. It finds applications in almost every industry where you have parts, where you have materials being used to manufacture parts. You could build rockets using additive manufacturing. You could build tubes. You could build complex heat exchangers. In
So
our
it's very universal.
It is very universal, right? Because there's a lot of processes that that fall under the purview of additive manufacturing as a process. In our case, the tubes that we used were made using a process called selective laser melting. But that's not the only additive manufacturing process out there. There's a lot of them, and there's a lot of flexibility when it comes to the materials that you can work with. Metal additive manufacturing is in fact a relatively upcoming new field, whereas polymers have been in use for a lot of 3D printing, which is also another name for additive manufacturing. Polymers have also been conventionally used, so it's not really limited to industries. It finds applications almost everywhere.
That's great to hear. So just to follow up with that, what new opportunities would you expect in industry who will benefit from SilcoTek 2000 coating that can be applied to additively manufactured part that intrinsically would have higher fouling susceptibilities, but then in combination with a coating might make it a better option than a conventionally manufactured part?
I'll let Deepto answer this in context of the jet fuel fouling experiments, but I can tell you a little bit of about my own experience. I've used the same coating for other applications where fouling occurs. So fouling as a process, it's not of one kind. There's different kinds of fouling, right? There could be inorganic fouling. There could be fouling by jet fuel oxidation. There's also biofouling. But what or a common feature of every process or every process where you encounter fouling is that to mitigate fouling, anti-fouling coatings have to be smooth, and then they have to be low surface energy or relatively lower surface energy than your substrate. So I've used Silcolloid coatings for mitigating fouling of inorganics, where you have, for example, seawater flowing in through heat exchangers in power plants or in desalination plants. And then based on temperature gradients and temperature differences, you have seawater, the salt in the water coming out and getting, depositing on the walls. So applications such as those, in addition to jet fuel that I'll let Deepto talk about in a minute, can, benefit from coatings such as these, which make your surface smoother and, prevent fouling.
I think to add what Taran said, I completely agree with him. Like these findings can benefit people who need surfaces that can be resistive to different kind of foulings or scaling, especially in industrial applications where you need to have like clean surfaces so that we have maximum heat transfer in those areas. So these findings can benefit them. And what I have worked with is the jet fuel work. So it will benefit the industries where the areas like the aerospace industry, where they need efficient heat transfer within the system. and which might lead to low maintenance cost and also help them prevent like detrimental effects on the whole propulsion system.
That's great. So that's the value of this, the coating in combination with the parts that you're studying for the industries. Lower cost, flexibility, and extended lifetime.
Yeah.
It's very exciting. So I know you guys are a research group. There's always more experiments to do. So what are the next steps after the publication of this recent paper, and what's next for research?
So following the publication of the paper, our future research will mainly focus on like further optimizing the coating properties to like enhance durability and long-term performance. And also additional studies may investigate multi-layer coatings or hybrid material solutions, and also chemical modifications to enhance like the resistance against oxidation and fouling. Another direction is includes like evaluating different post-processing techniques such as like electropolishing to smoothen these additively manufactured surfaces, which can further reduce like the fouling susceptibility.
That's excellent. So just to close on with the interview, what coating properties might be needed to solve additional challenges in your field of work, in addition to what SilcoTek 2000 has already demonstrated? So that also gives us ideas on our research.
Yeah, I could take that first. So as a research group, we are focused on a lot of thermal applications and a lot of chemical material-based applications, and we work with a lot of coatings. But ultimately, all of our coatings have to be functional, they have to be scalable, and they also have to be durable. Uh, if I go into each of these briefly, functionality to us means different applications, such as a smooth surface, such as hydrophilicity or hydrophobicity or self-cleaning properties. Durability means the ability to use our coatings or our parts for extended lifetimes. We don't want maintenance to, or we don't want maintenance required every week or every month. We want our past parts to last years, or at least as long as timeframes where regular scheduled maintenances are in place. Scalability wise, which is the other pillar of our research, these coatings have to be applicable to arbitrarily shaped parts and geometries, because heat exchangers are not just tubes, heat exchangers are not just flat surfaces. Scalability also means applicability, or the ability to manufacture parts at a faster rate. Sometimes scalability could mean simpler processes, such as not requiring vacuum chambers or chemical vapor deposition, or just using simple processes such as dip coating. So those
In
are
situ application.
right.
You can just
Those,
apply the coating on site.
right. You could spray it. You could dip coat it, or take a paintbrush and apply the coating wherever you want to. So those are kind of the additional properties that we desire as researchers to solve a whole lot of problems that we face in our research.
I think the future coatings like could incorporate self-cleaning properties or like catalytic functionality, so that it can actively like break down the deposits whenever it's becoming detrimental.
Well, very insightful. Thank you again, Dipto, Taran, and Jung Bin for joining us to discuss your research.